Welcome back to the channel. I know it's been a little while since I posted my last video, coming up on almost a year, but today I will be making bromine, elemental bromine, and my source of bromide ions to begin the experiment will be sodium bromide. Before we get into this, I'd just like to say I wouldn't really recommend repeating anything you see in this video, as bromine is very toxic, hard to contain, and can burn the eyes and lungs very easily and is unpleasant in general. Without any further ado, you can see that there were approximately 108 grams of sodium bromide used in this experiment, which corresponds to just a little bit more than a mole. Without getting too far into this, I'd also like to say that this was a qualitative experiment, not a quantitative. I wasn't trying to produce a definite amount of bromine. I was just trying to prove and collect a reasonable sample of bromine. As you can see, the bromide salt was then added to a 500 milliliter flask, which took a little bit of work as some of the salt had clumped together during its time being stored. After I managed to get everything in the flask, approximately 100 milliliters of water was used to dissolve the bromide and also to wash out the solid addition funnel. Not all of the salt dissolved in this amount of water, but I was trying to keep the bromide salt very concentrated, as the next step in producing the bromine was to react the sodium bromide with sulfuric acid, which produces hydrobromic acid, which can then be oxidized into bromine. The sulfuric acid I was using was not particularly pure, and I used about 150 milliliters of it, which was of unknown concentration. You'll see that immediately upon the addition of the sulfuric acid, the solution takes on a ruddy red color, which is due to some bromine being oxidized due to the presence of sulfuric acid, which is a reasonably strong oxidizer in its own right and has the ability to oxidize a small amount of bromide into bromine. Sulfuric acid was mainly used due to its high boiling point, meaning that it wouldn't distill over with the hydrobromic acid and contaminate it. At this point, a distillation was necessary to remove the hydrobromic acid from any excess sulfuric acid and any remaining salts, such as sodium bromide or sodium sulfate. These salts could cause issues later in the reaction, and it's better just to remove them now. The hot plate was turned on to approximately 380 degrees Celsius, which is far higher than the about 120 degree boiling point of hydrobromic acid, but it was necessary to heat the flask up this hot to ensure that most of the hydrobromic acid came over, which was kind of difficult as the glassware was losing a lot of heat. At this point, the distillation was mostly complete, as nothing else would distill over. What you're seeing here is a combination of sulfuric acid, sodium sulfate, a small amount of sodium bromide, and possibly hydrobromic acid, most of which distilled over into the collection flask, and it turned out to be approximately 250 milliliters. Immediately after turning the hot plate off, the sodium sulfate in the distillation flask began to crystallize. Initially, I was kind of concerned that it would expand and crack my glassware, but it ended up being alright. I tried to capture the formation of some of the crystals on my camera, but it didn't really do it justice. It was far better to see in person. After most of them had solidified, I broke them up, and as you can see, there's very little liquid, which means that almost all of the acid was distilled over. With the hydrobromic acid procured, you can see it in the right flask. It was oxidized using TCCA tablets and hydrochloric acid, which produces chlorine gas, which was bubbled through the solution, oxidizing the hydrobromic acid into elemental bromine, which gives it the red color. After about 45 minutes or so, the reaction appeared mostly complete, and I stopped bubbling chlorine gas through the mixture. It was now time to separate the elemental bromine from the hydrochloric acid and water mixture. This was done using a separatory funnel. As you can see, the bromine sinks to the bottom of the separatory funnel as it is denser than the remaining solution, and bromine is one of the only two elements that at room temperature is a liquid aside from mercury. At the top of the separatory funnel, you can see that there's a sort of reddish vapor filling the headspace between the liquid and the ground glass fitting. Bromine is a very, very noxious gas, and that is one of the reasons that it's so difficult to store and work with is its extreme volatility, meaning that it vaporizes into a gas very, very easily. That's one of the main reasons that this experiment was done outside, particularly the second half using chlorine as an oxidizing agent. Chlorine was used in World War I in the trenches, and bromine has a lot of the same properties, except it's almost more dangerous than chlorine gas as it's a liquid, and thus it's more concentrated than gaseous chlorine. At this point, we have mostly pure liquid bromine, although it does contain a small amount of water. To remove this water, the bromine was poured back into the separatory funnel, and a healthy amount of sulfuric acid was added. Sulfuric acid is extremely hygroscopic or water-loving and will absorb most of the water from the bromine. Here you'll see me capping and venting the bromine inside of the separatory funnel numerous times. Once the bromine is settled to the bottom after the washing step, it's practically ready for storage. For me, I thought that the safest mode of storage would be to use some glass ampules that I had prepared. Unfortunately, one of the ampules that I made didn't seal completely, and so my entire yield was 1 ampule of pure bromine, as you'll see later in the video. This was all I really wanted, however, as I didn't want to have a bunch of this stuff around because it's pretty dangerous, and I just needed a sample for my periodic table. Anyways, I'd like to thank you for watching, and I will end this clip with a reaction between a small piece of sodium and the broken ampule that didn't seal correctly.